So in this part of the lectures, we'll discuss two classes of no-go results that one can prove for NLE theories. So the first type of no-go results will be the ones that forbid the existence of the electromagnetic solitons. And the second type will be the ones that constrain the possibility of black hole regularization using nonlinear electrodynamic fields. So we can start with the first type, the no soliton theorems. So one may ask whether localized finite energy equilibrium solutions exist in general relativity. And the answer to this question is yes. Black hole solutions satisfy all of these requirements. And then we can ask what if we demand regularity and absence of horizon? Then one gets particle-like solutions that we call solitons. And Wheeler's geons, where geon stands for gravitational electromagnetic entity, they can be regarded as the examples of solitons. So one may imagine them as some lumps of waves that are held together by their own gravitational pull. And it has also been shown that if we demand that the space-time is static, asymptotically flat, regular, has finite energy, and we are dealing with a vacuum case in Einstein theory, then the only such space-time is Minkowski space-time, and this statement is known as the absence of purely gravitational solitons. And now one may ask if we could find configurations like this in some other theories. Of course, in our case, we will be interested in the existence of the electromagnetic solitons. So now we have to say precisely what the electromagnetic soliton is. So we're looking at strictly stationary, which means that there are no horizons in this space-time, because the Killing vector field, it changes its causal behavior either on the beyond the horizon, if we're dealing with static black holes, or in the ergo regions of rotating black holes. So besides stationarity, we have the condition of regularity and asymptotical flatness. And the associated electromagnetic field is non-trivial. And it is known that such configurations are absent in Einstein-Maxwell case. So our question was, can we generalize these results to Einstein NLE theories? And the idea of the proofs is relatively simple. It has been also used in proofs of uniqueness results. So the idea is the following. Construct some convenient quantity which has a defined sign. So here I would, let's say that it is non-positive, but its integral over some domain is non-negative, then we can conclude that this quantity has to vanish. And we'll see how that exactly works in the theorems. So what we did, we managed to prove two results that hold under slightly different conditions. So theorem 1 holds for static spacetimes, while theorem 2 holds for stationary, so it is in that regard more general. To prove the first result, we used the null energy condition, which in the NLE case holds if and only if LF is less than or equal to 0. LF, just as a reminder, it is derivative of Lagrangian with respect to the invariant F. Well, to prove the second result, we had to use dominant energy condition. So here LF has to be less than or equal to 0, but also the same inequality has to hold for the trace of energy momentum tensor. Theorem 1 will hold for an arbitrary gravitational action as long as we are considering minimal coupling of gravitational and electromagnetic sectors. While to prove the second result, we explicitly used Einstein's equation, so it will hold for Einstein-Hilbert action. And we also had to rely on positive energy theorem. And the conclusion in both cases is that the electromagnetic field is either trivial, which is the same result as we have in the Maxwell case, or it could be also stealth. So we have seen that in the Anton case, we could in principle have stealth field configurations which do not contribute to the energy momentum tensor. So that is precisely why such fields can evade some of the no-go results. So the main ingredients of no-Soliton theorems are divergence identities, plus energy conditions, and a smaller number of technical assumptions. And these technical assumptions are the following. So we will assume that the electromagnetic field inherits the symmetries of the space-time, so the Lie derivative of f is equal to 0. And we will also assume that the manifold is simply connected. So we will use these facts to introduce scalar potentials. Then we also have to assume that certain fall-off conditions hold. So we are dealing with the asymptotically flat space-time. And also we impose some fall-off conditions for the fields themselves. And we will also assume that the Lagrangian density obeys Maxwell's weak field limit. So we will need these two conditions to eliminate the boundary terms that will appear. And lastly, so the last condition, it basically says that the space-time is strictly stationary, so the norm of Killing vector field, time Killing vector field A, will be equal to minus function v, and so this v will be positive. Okay, and so if you have any questions, also feel free to interrupt whenever you want. So to prove the results, we need some auxiliary results first. So one can introduce twist one form, which is defined in this way. So it will vanish in static spacetimes. And due to the technical assumptions 1 and 2, we can introduce scalar potentials. So we have the electromagnetic scalar potentials, phi and psi, that we discussed yesterday. And we may also introduce further two scalar potentials that are related to the twist form. And these are UH and UE. Because you can check that. First, you need to show that the omega is equal to E wedge magnetic form H. And then you can see that the combination of omega plus 4 phi H will be the closed form. And the same holds for a combination of omega minus 4 psi times. And then also you can try to derive these divergence identities. Here, what you can immediately notice is they will become much more simple in static spacetimes when the twist form vanishes. So the right-hand side will be equal to 0 in this case. And now we may move on to the proof of the first result. So, using the auxiliary divergence identities that we have seen on the slide before, you can see that divergence of this combination of potential of field here D, here B, divided by V, will give us something that will prove to be useful. Because now if we take sum of these two expressions, what we are left with on the right-hand side is LF, squares of the fields divided by function V, which was related to the norm of the Bokulic vector field. And then why is that useful? Well, because LF, we can control it, its sign, if we impose energy conditions. V has a defined sign due to strict stationarity. And then one proceeds by integrating this expression over space like hypersurface sigma, that is asymptotically flat. And then you can see that whenever this form alpha, if it's symmetry inheriting, then this divergence term, it can be translated into a boundary integral. And then, because of the fall-off conditions that we assumed, we can get rid of this boundary term. Okay. And then what we are left with is this expression here. So we have this integral over sigma of squares of the fields, LF and V. Now, V is positive. Due to null energy condition, LF is less than or equal to 0. And also what you can notice is that E and B both cannot be causal. So now if you remember, E and B were contractions of F and Hodge dual of F with Bokulic vector field. And then if you perform another contraction, it will identically vanish due to the properties of differential forms. So, and then since K vector field is time-like, strictly time-like, and it's when contracted with E and B, it gives 0. This means that E and B have to be space-like. That is the only option, so E and B are not causal. And then what one can conclude, so now we have a quantity that has that doesn't change sign under the integral. So we can conclude that whenever LF is non-zero, then E and B have to be 0, and we arrive at the situation when we have trivial electromagnetic field. But if LF is equal to 0, then the field can be either trivial, or we could be dealing with stealth fields. Now we may move on to the proof of the second result. So we start from the same divergence identities, but now they will be more involved because now we are no longer in the static case. The space-time now is stationary, so the twist one form omega, it will not vanish. And then what one can do is define this quantity here denoted by W. And it's very useful because its divergence can be related, as you can see here, to the trace of energy momentum tensor, and this left side, which contains norm of omega and contraction of Ricci tensor with Bokulic vector fields. And this left side actually can be related to Comer's mass. That is why this expression is useful. And also, if you want, you can try to actually get this expression using Einstein's field equation. And now what I said, so this left side will appear in the expression for Comer's mass, along with this term that will turn into the boundary term. And as well, if you wish, you can try to actually obtain this expression. So first you need to prove this relationship here, then you perform contraction with Bokulic vector field K, and you should be able to get to this expression stated here. And then again, what happens is that this term will drop because of the assumed fall of conditions. So when combined with this expression from the former slide, we can express Homer's mass as divergence of quantity W and this trace of energy momentum tensor term. And now again, what happens is divergence will become a boundary term, and it will not contribute to the Homer's mass due to the fall of conditions, while the second term will be non-positive due to the assumed dominant energy condition. But on the other hand, positive energy theorem says that M has to be greater than or equal to 0. So here we are led to the conclusion that M is equal to 0. And then by positive energy theorem, space-time is Minkowski space-time. And we're back at the case of either having trivial electromagnetic field or having stealth field configurations. And here one may try to further generalize these results. I don't know if I can move this a bit higher, because now the footnote cannot be seen. Okay, it's not so important. So one can consider two possible ways of generalizing these results. Here we will be focused on static case only. And one way is to consider higher dimensional theories. But here we have problem that the invariant G will no longer be a scalar because it was defined with Hodge theorem of F. But we can solve this problem by restricting our attention to F plus Lagrangians only. And the related problem is that B will no longer be a 1 form because it was also defined as a contraction with Hodge theorem of F. So the best that we could do in this case is to conclude that whenever LF is not equal to 0, then the electric field has to be trivial, because the other divergence identity that includes field D will hold even in higher dimensional cases. Another possibility is to consider a more general theory, so to add some charged matter, we consider the case with complex scalar field. So the total Lagrangian consists of an LE contribution, this covariant gauge derivative term, and some scalar potential term. But here, the main obstacle is the fact that to generalize Maxwell's equation, the one with Hodge field of form Z, is no longer closed. So there is a current term on the right-hand side. And then consequently, form H will no longer be closed in this case. So what we can do here, only if we impose some additional assumptions like that K wet J is equal to 0, which will then eliminate the right-hand side, and H will be a closed form again. So if we assume that, and also that the scalar field is symmetry inheriting, then we can again conclude that the electromagnetic field will be trivial. And after this analysis, one can ask some questions. So, how do we deal with a manifold that is not simply connected? How do we define potentials in this way? Also, what happens with more general NLE theories, those that do not obey Maxwell's weak field limit? How do we then eliminate the boundary terms? Now, when we consider generalizations, we only took into account higher dimensional cases. That is because in the lower dimensional cases, the natural fall-off condition of the scalar potential is logarithmic. And then again, we would have problems with the elimination of the boundary terms. And of course, one may ask, can we consider other types of matter coupled to the NLE Lagrangian and see if the conclusions are altered in this case. Okay, so if there are no any questions, then we can move on to the second type of no-go results. So now we will discuss the regularity theorems. And as you have heard today, so the story starts with Bardeen black hole and its interpretation. So Bardeen proposed a regular black hole solution. So this metric, it corresponds to a spherically symmetric black hole. And here you can see the additional parameter G, which actually serves as a regularizing parameter in this black hole. But the origin of this black hole was not clear. So its source was unknown for a long time. And much later, Einbeld and Garcia, they noticed that this solution can be obtained from an NLE theory of this form. And then they identified G with black hole's magnetic charge and mu with black hole's mass. So, however, there are some unwanted features that this Lagrangian has, because if you take a look, here one has square root of invariant f. So for magnetic configurations, this will be well defined, but otherwise not. Also, it doesn't obey Maxwell's weak field limit. And another strange feature is that the parameters of the solution appear explicitly in the Lagrangian. So here you can see explicitly mass and black hole's magnetic charge, which is a feature that we do not expect from a fundamental theory to have. And also you may probably wonder how did they manage to actually derive this form of Lagrangian, and that is a point that we will discuss a bit later. This black hole and its interpretation naturally raises the question, so how general this prospect is? When can we expect to get regular black holes in nonlinear electrodynamics? And this question was partially addressed by Bronikov in his paper from 2001. So he assumed that space-time is spherically symmetric, and that the Lagrangian belongs to the F class, and that it obeys Maxwell's weak field limit. And he concluded two things, and that is that no locally regular space-time can exist whenever the electric charge is non-vanishing. And another thing, and that is if the limit of this Lagrangian, when F goes to infinity, exists and is finite, then one can find regular solutions with magnetic charge. And indeed, many examples of such Lagrangians have been constructed, such as the rational and exponential one that I mentioned in the talk yesterday. But so the problem here is that these Lagrangians do not come from any more fundamental theory, as was the case with Heisenberg and Horn-Infeld Lagrangians. And also here, in order to get regular black holes, one has to rely on the existence of magnetic monopoles, which is also a bit tricky. So the idea of the proofs is very simple. One has to translate curvature invariance to matter invariance using Einstein's equations. So in this way, we can relate Ricci scalar to the trace of energy momentum tensor, and this term, the scalar, which we'll call Ricci squared, to the square of energy momentum tensor. And then if the space-time is regular, this means that the curvature invariants have to be bounded, and then this implies that also trace and the energy momentum tensor squared, they also have to be bounded. So here one has to be careful, because if all the curvature invariants are bounded, this will not imply that we have regular space-time, because you can find examples of space-times in which they all vanish, but space-time is geodetically incomplete, or one can construct some even more pathological cases. But what we can say is that if we manage to find unbounded curvature scalar, at least one, then for sure we know that we are dealing with a singular space-time. So these restrictions are good enough to give a no-go result. And of course our question was, can we generalize these results to FG class Lagrangians? Because Goni communities analysis, he covered F class. So first question was, how many independent invariants do we have at disposal? First, we calculated this contraction of the energy momentum tensor, so it is equal to trace squared and terms of the form L of times S squared, L times G squared. And then the question was, can we use contractions of more energy momentum tensors in order to construct new invariants? And in fact, we were even able to derive a general formula that will hold for contractions of an arbitrary number of energy momentum tensors. So its form is less important, but what you can see from it is that it will actually it will be reduced to higher powers of those basic ones, so trace, L times F, and L times G. So here, the important message is you cannot construct any new independent electromagnetic invariants from which you could extract some further constraints. So we have to rely then on trace, L times F, and L times G. So the general setup is the following. We took the standard form of the metric of spherical symmetric space-time. And here notice that with this choice, we didn't lose any generality, because this condition on the energy momentum tensor that guarantees that GTT times VR is equal to -1 is satisfied for analytic theories. Also, you can check that if we define the electric and magnetic forms with respect to Killing vector K, time-wide Killing vector field, then the electromagnetic field tensor attains this form, so it has the electric component and magnetic one. The electromagnetic invariance can be expressed in terms of fields, and also one can integrate generalize Maxwell's equations. And the integration constants are fixed by the definition of covert charges. So now we can move on and see what happens in the electric case. So when the black hole only has the electric charge and we set the magnetic charge to 0. So our first theorem holds for FG class and Lagrangians, which have Maxwell's weak field limit, and the conclusion here is that Ricci scalar and Ricci squared cannot be both bounded as radial coordinate goes to 0. So this singularity will be still present. And then we can also go through the proof, because it's very simple and it illustrates the idea well. So the first Maxwell's equation will tell us that the magnetic field is absent. It was directly proportional to a magnetic charge, which is 0 in this case. While the second one can be rearranged in this way. And now we said that if the space-time is regular, then LF times F term has to be bounded. Then the whole right-hand side remains bounded. Then the same has to hold for the left-hand side. And then this fixes the behavior of invariant F as R goes to 0. So it will also go to 0 with this power of R. But then what we can see on the other hand is that LF will then be unbounded as R goes to 0. And this is direct contradiction with the assumed Maxwell's weak field limit. And here in this case, this contradiction is quite obvious because the limit in which R goes to 0, it coincides with weak field limit when invariants also go to 0. G is trivial in this case equal to 0 because the magnetic field is absent. Before continuing my technical problems. Yeah, so now before moving to FG class, we can revisit F class theories and discuss Diomic case, in which we have both charges, Q and E. And here one can prove a result that holds for all F class annular Lagrangians, and the conclusion again is that the space-time will not be regular. Proof is very simple, again follows from Maxwell's equation, just written in the appropriate form. And again, we know that in regular space-time, LF times G has to remain bounded. Then the whole left side is bounded, but the right-hand side of the equation is manifestly unbounded as R goes to 0. So here we obtain contradiction. And such theories will not lead to regular symmetric black holes. And now if we move on to FG class again and consider Ionic and magnetic cases, you can notice one obstacle, and that is the fact that we lose the opportunity to directly test the Maxwell's weak field limit. And this will be obvious if you rewrite invariant F in terms of invariant G. Now you can see that as you send R to 0, F and G cannot both go to 0. And if we want to compare with Maxwell's weak field limit, we need both F and G to go to 0. But then we managed to prove no-go results for some specific FG class Lagrangians, which consists of Maxwell term plus some function of invariants F and G. And here we'll not go through the proofs of these results, we'll just go through the summary. So what we managed to prove is that a quadratic Lagrangian of this form that is inspired by Euler-Heisenberg Lagrangian, it will not give regular Ionic or magnetic black holes. And the same holds for the Lagrangian that is equal to Maxwell term plus some function of invariant G. For the Lagrangian that is equal to Maxwell term plus invariant F up to some power S and invariant G up to some power U, we managed to prove that the Ionic configurations will not be regular. Well, for magnetic we couldn't give an explicit no-go result. And we also managed to prove in this way, without solving explicitly equations of motion, that Born infield and mod max Lagrangians do not lead to regular Ionic or magnetic black holes. So now here the main open question is how can we extend these results to cover a broader family of FG class Lagrangians? Because here we had to resort to analyzing them case by case. So the question is, can we give some more universal result? Also, one could ask what happens if instead of Einstein's theory we use some modified gravitational action? Can we then such theory of gravity get regular black hole solutions with NLE Lagranges. Or also one can consider a more general case of non-minimal coupling of gravity and NLE. However, the equations will be much more involved in this case. And also, it's not clear how successful NLE fields are in removing singularities of other types of spacetimes. So I mentioned that in cosmology, some models may remove the initial singularity, but again, these analyses were also done on a case-by-case basis. There is no some more universal result that would cover a whole class of NLE theories. And now I would like to explain the so-called reverse engineering procedure. So here you can, from imposed metric function, deduce the form of Lagrangian. And that is precisely how you can then, from Bardeen black hole, reconstruct the unbounded inertia Lagrangian. Of course, this method has its limitations. It will work only in some specific scenarios when the Einstein-NLE equations are simplified enough. So now let's focus on, again, on spherically symmetric spacetime. And the metric function, we'll write it in the form as 1 minus 2 times function m divided by r. Also, we'll consider F-class Lagrangians, and we will consider the case with a magnetic field only. And then you can check that Einstein-NLE equations are reduced to the following system. And now if you take a closer look, you can see that basically the first equation is what you need to reconstruct the Lagrangian. And that is because if we have magnetic field only, we know how does magnetic field, how does it look. So we can express radial coordinate in terms of the invariant F. So what remains is just to plug in the metric function, calculate the derivative of m divided by r squared, and then evaluate it for r given by this expression here. And also you can see that by this construction, another Einstein-NLE equation, this one, it will automatically be satisfied. So this will really be the solution of the theory. But also with this procedure, you don't know what will be the form of the Lagrangian that you will get. It might be something very unphysical. And we try to address this question and try to find a more physically plausible model using this reverse engineering procedure. So we consider a Lagrangian that can be decomposed in a function that depends on invariant f only, and another function that depends on invariant g. And we have shown that if you take this simple metric function, this rational one, then if you fix the constants appropriately, this function j will actually, in the weak field limit, behave as Euler-Heisenberg Lagrangian. And from that demand, also we can reconstruct then function k. But also this Lagrangian has one unwanted feature, and that is that mass and charge will not be independent. And actually, this is a feature that will generally be present in such regular black hole solutions with magnetic charge. So mass and charge have to be somehow fine-tuned in order to give regular black hole solution. Now we can illustrate this again on the example of a Bardeen black hole. Now let's forget how the Lagrangian was constructed. Let's say that the theory is now proposed with some fundamental parameters, lambda 1 and lambda 2. For now, we do not know if they're related to mass and charges of the actual black hole solution. And then, if you go back to Einstein-Henle equations, and you integrate this first one, on the left side you will get mass, and on the right side you will get charge, and multiplied and divided by these constants of the theory. So now you can see that mass and charge are actually not independent, they're related by this expression here. Of course, then you can adjust the parameters to hide it, but then you will have that the mass and charge will appear explicitly in the Lagrangians. But actually, these two problems are related. So now, to sum up, in order to obtain a regular black hole solution in general theory of nonlinear electrodynamics, you either have to give up on having the Lagrangian database Maxwell's weak field limit, because this is generally not compatible with the existence of electric charge, or you can introduce the magnetic charge, but then either mass and charge will appear explicitly in the Lagrangian, or mass and charge will they won't be independent, but they will be related to the parameters of Lagrangian, but interactive. And here we can stop for today.
So we have time for questions.
So thank you for the very nice short course. So my question is actually about the number of theorems, in particular about the Bernoulli theorem. So in his theorem, he assumed that the Lagrangian density behaves as the Maxwell theory in the far field, right? So the L of F will behave like F in the far field. So my question is, what about the behavior at the core of the solution? He also assumed that it would behave as the Maxwell's theory at the core.
Yeah, because basically what happens is that if you want to get a regular solution, then you immediately know that F will go to 0, also at the core. And then you can immediately compare this to, you may compare the behavior of LF in this limit. So yeah, basically, yeah.
Okay, so that's what I actually was thinking about. It wouldn't be possible to actually have this Maxwell weak field limit at a far field, but pure regular black hole solutions where the behavior of the magnetic charge solutions is different from the Maxwell case at the core, or we actually need to have this Maxwell-like behavior at the core to obtain regular black hole solutions.
You mean, so do we need to have Maxwell behavior for magnetic black hole to get regular?
Infinity and at the core.
Well, so you, with such Lagrangians, both at the core and at infinity, you can get a regular black hole. But you can also, with magnetic solutions, you can have Lagrangians that do not obey Maxwell's weak field limit, and they will give regular solutions. Yeah, it's only, so Maxwell's weak field limit is interesting from the physical standpoint. That's why we impose that.
And the other way around is also possible.
By other way around, you mean?
Like, we do not have this Maxwell-like behavior at the core, but we still have it at infinity.
Oh, so, okay, now I see.
That's
Okay, to determine whether there is Maxwell limit, first we need to determine how does Lagrangian behave with respect to invariant f. And then later we can see what happens actually when we express it in terms of coordinates. In the magnetic ACI, it's simple because the magnetic field behaves, it's very symmetric times c divided by r squared. So here we can have this intuition about the behavior.
Okay, yeah, my curiosity is just the possibilities to circumvent or overpass the theorem. So I think.
And with the electric charge, unfortunately, there is no any space to get a very good black holes with Maxwell's feature limit. Of course, there are the black holes electrically charged, but then they do not obey Maxwell's feature limit.
Thank you very much.
Thank you very much.
Thank you very much. I think we have time for one more question. So if not, let's take Anna again.